Hello everyone and welcome to this course. We shall be building an FHE-based biological age prediction system using the DNA methylation data, and the system will be powered by Zama AI's ConcreteML. Now, first things first, biological age as access through the domain of epigenetics refers to the measure of a person's physiological age based on their physiological aging based on their DNA methylation patterns rather than their chronological age. If, like me, you have no background in epigenetics, we shall go through some key terms which are fundamental in understanding how we could make use of DNA data to predict biological age. We shall start with understanding DNA methylation. Then we'll dive into fully understanding globally the concept of fully homomorphic encryption. We'll look at existing DNA methylation data sets. Then we'll dive into data processing, modeling, training, and deployment. So let's get straight away into DNA methylation. But before looking at that, let's understand what a DNA is at a higher level. Now, a DNA is a very long instruction manual for building and running your body. The domain of epigenetics, on the other hand, is a layer on top of this instruction manual which tells the cells or your body cells how to interact with this instruction manual. Now, when we talk of DNA methylation, is actually getting into the cytosine, that's this chemical in our DNA. You have here cytosine, thymine, guanine, adenosine, and then sugar phosphate backbone. So we get into this cytosine, and then we include or we add this methyl group. Now, a methyl group is simply composed of a carbon atom and 3 hydrogen atoms. When a methyl group is added to the cytosine, as we've seen in this way, this is the process of DNA methylation. Now, this often happens in areas of the DNA called the CPG islands. Now, the C stands for cytosine. You have your cytosine. Let's pick up the pen. Turn on the pen. So here we have the cytosine here. Then the P is for phosphate and the G is for guanine. So we have these islands where we have the C, the P, and this G's stacked up together, and it is in these islands that we have this methylation occurring. You could see here in this DNA strand this methyl groups in red. See the different methyl groups in red, which shows that our DNA has undergone the process of methylation. The way we measure the degree of methylation at a given site is by making use of methylation arrays. So methylation arrays essentially are tiny chips with millions of probes, and each probe checks for a specific CPG site for methylation. And once we get this information, we have generally better values or M values for each site. So better values, we have values ranging generally between 0 and 1, where at 0, or for a better value of 0, simply means that that site is unmethylated, and 1 means it's fully methylated. And obviously values between 0 and 1 show the degree to which it's methylated. Then the M values could be positive or negative, and the larger the value means a more methylated site, and the more negative the value means it's a less methylated site. Generally, we make use of the better values, and that's what we're going to be using in this course. It should be noted that as you age, the degree of methylation on each and every site varies, and it is thanks to this information that we could build out machine learning models which will take this information, or we should take the inputs, like for this one, for example, this DNA methylated data and the person's corresponding age, and then train a machine learning model based on many of these input output pairs, such that when we have an input like this one, then we could infer the person's age. Let's now understand at a higher level fully homomorphic encryption with Zama AI's ConcreteML. So the previous model we had was a scikit-learn XGB model, And now we replace that with a concrete ML model. Now, the reason why we want to do this is simple. Suppose we have input data, and we have this input data is at the level of the client, and then we have a server right here. Then you want to, let's copy take this. Then you want to pass this into or you want to carry out some processing. After carrying out this processing, you send this to the server, let's say some remote server, and then you have a model which takes in this input and then sends back that output to the client, like say a predicted age, let's say an age of 19, for example. The problem with this method is that you have people's private data, which is sent to a remote server. And we understand that sending this kind of information through a network to some remote server somewhere in the world can lead to this private and personal information to be tampered with. And that's not what we want. So that's where fully homomorphic encryption comes to play. So with fully homomorphic encryption, instead of sending this raw data or this person's data over to the server for processing or for prediction, what we are going to do is slightly different. Shall start by encrypting this data. Then we'll pass this encrypted data to over the network to this FHE based ConcreteML machine learning model, which is capable of carrying out predictions even on encrypted data. So this time around, we are not sending our raw data. We are instead sending encrypted or the encrypted version of our data. Now, once we have this encrypted version, we pass into the model. It carries out this prediction at the level of the client. That's, let's say, the user's mobile phone or some PC. This is going to be decrypted again, and then we're going to have our final output. So instead of taking this raw data and sending directly into some model, into a server, and allowing this information to be tampered with, we are going to pass this through encryption, and then it's only the encrypted version that's been sent, and we have the keys or the necessary keys to decrypt this information, and then we have our output. Zama AI is this company which built the ConcreteML library, which is or which focuses on privacy preserving machine learning, and that's exactly what we are working on in this course. Now, before we move on to the modeling and training of our data, we'll first of all look at existing DNA methylation datasets. The dataset we shall be using is the one used by the authors of this paper, a pan-tissue DNA methylation epigenetic clock based on deep learning by Lucas Paulo de Lima Camilo et al. So in this paper, let's search for dataset. In this paper, they have this data set, which we're going to check out the details. Let's open that out. There we go. So they have this data set, and they'll say they split this up into train, validation, and test. And you see you have so many different sections. So here we have this GSE 27317, and it's composed of newborn umbilical cord Buffy code samples. All samples were recorded as having 0 age. The platform used was Illumina's Infinium 27K human methylation bed chip. So it's similar to this here, what we have seen here. So this this Illumina chip right here is the kind of chip which was used in extracting this information or getting this DNA methylation data. Then we have this other one where we have whole body samples in schizophrenia patients and healthy subjects. Non-healthy patient samples were separated for further analysis and not included in training, validation, or testing. The platform used was still Illumina's Infinium 27K human methylation bed chip. And that's it. So they outline all these different sub data sets, which are all combined or could be combined to form one full data set. So that's it. Now, if you check out here, they specify the code. So we could get into the code for this. Let's get into the README. They have this code, and in the code, they specify the drive which contains the data. So here again in the code is the specific. They say here that they have the DNA methylation better values from Illumina arrays 27K, 450K, or EPIC, and the selection of 20,318 specific CPG sites provided in the cpgsites.csv file. Anyways, let's check out this Google Drive repository. If you check that out, and if we look at this pre-processed data here, and then let's open up the train. You see, you have all those different files or all those different sub data sets which were mentioned in this file right here. So all the details are actually mentioned here, and then here you have the data set itself. So let's get back there. Here you have the data set itself, and that's exactly what we are going to be using in this course to train our model. Now, making use of all those different file names, we create this dataset list right here. Now, this dataset list created, we will now go through each and every pickle file in our dataset. Go through each and every pickle file. See here, we go through this dataset list, and then we'll read this pickle file and create a pandas data frame. Once this data frame is created, we're going to put this into our all data frame list. Then once we have that, we'll now just simply save this as a CSV. So we'll go through this, save as this CSV. We specify the file path. That's it here. It's already saved. And then the combined data frame is simply concatenating all the data frames in this all df list, and then we used the toCSV method to save this as a CSV. Then after we load this again, and then we have our final this output. Now this output is a combination of about 4 of these different data frames, which we printed out here. Notice how when I is greater than 2, we just came out of this loop. Now what you want to do is take this off actually and run this all through. But because it takes a bit much time, we're going to leave that out for now. But you could feel free to check to test that out. And that's it. So once you have that, you let's get back here, you will have this kind of output. So you see that our data set is now, because we've combined 4 different sub data sets, and we have 348 rows. Now after combining all the data sets, you should have about 8,000 rows. Now it's quite heavy. Look at this, it's about 140 megabytes, and that's because we have so many columns. You see here we have 21,372 columns. Now let's look at each and every column. First of all, the data set is specified. Notice how we have this data set, and we have this other data set and some other data sets in the middle. Then we have the tissue type. See, specify the tissue type. We have the age, which is very important. We have the gender. And then we now have each and every CPG site methylation data. So you see how we have all these different values for each and every CPG site. So we go from the site or site 1 to site 21,372 minus this. So this is about 21,368. So we have 21,368 different sites, and then they have each and every one of them have their own values and their corresponding age to match with that. And if you do this for all the different, as we've said already, you should have about 8,000. So what I'm going to do is I'm just going to comment all this part, because I've already done this myself. And this was just to show you exactly how I obtained my final data set or my final CSV file. And then from there, we'll just move on with the code. So let's take all this off. And there we go. Okay, so let's reduce this data set creation part, and then we'll now run our pip install ConcreteML. So as we said already, Zama AI is responsible for this ConcreteML library, which is very important when we want to work with privacy preserving machine learning models. So the usual scikit-learn is will provide you the machine learning models, but if you want privacy preserving machine learning models which could be run on encrypted data, then the ConcreteML comes handy. So the first thing is to install ConcreteML. Once this is installed, we'll now start with the import. So we'll run this, and once that's done, we'll dive into the data loading. Now this data is found in this drive here. So I've combined all this into two. So we have the train data set, and then we have our test data set. So we place them in your train and test folders. In my case, I'm just going to simply get into my drive and then specify a given folder. Now we've looked at existing DNA methylation data sets and combined them into one. Let's dive into data processing. Once you load the full data set, you can now change directory into the one which contains the data set. And then you see how we load the train and the test data sets from our combined train CSV and our combined test CSVs. So that's how we obtain this output here. Now you see we have 8,050 rows as compared to previously where we had just a few rows. So now we have our full data set made of our full train data set made of 8,050 rows. Then in the pre-processing itself, we have this pre-process data method. What it does here is simple. We first of all separate the two parts, the patient data and the data itself. So if you look here, you find that we have the patient data. That's its first 4 columns. It's actually patient data, and then the actual data itself. That's the methylation, the degree of methylation in each CPG site, or the beta values represents all the other rows. Now let's get back here. You see we separate this two. We have the patient data, and then we have the patient data, and then we have the data itself, which is we drop in this patient data columns. Then we check for the number of better values or other better values that are not available. So after running this, we notice that, or we find that we have actually all our values are available. So we do not have a case where in our data set we have values that are not available. Now in the case where we had values that are not available, what we would use is this KNN imputer, which is going to make use of the k nearest neighbors to fill out those different positions where the data is not available. Now in our case, we all have, or we do not have those kinds of values, so we'll move on. Now we'll just need to combine the two. That's the patient data and our data itself, and that's it. So after running this, we have our same data set, and then we now move on to scaling. In the scaling, we actually tried out two methods. That's the robust scaler and the standard scaler, and we found out that the standard scaler performed better. Now making use of this is again quite simple. We have the info, that's the patient data, that's separated from the data itself. You see how we apply this drop method to take off those columns which contain just the patient data, and then we scale. The scaling is carried out on this better values. That's all this data. So we carry out the scaling using the standard scaler, as we said already. The standard scaler performed better. Then we make use of a scalar fit transform on our data. That's our data without the patient data. On our data itself, that's on our beta values. Then we have our output, that's the data itself that's been scaled. And then this time around, we discard the data set, the tissue type, and the gender, and we leave only the age. So we have this data ages here, which we obtain from just getting the age. So you see here, data will specify, we get just the age, we have data ages, and then we have the data scaled. So now this is like our input, this is our input, and this is our output. Now one other step we include is this obtain of the mean and the variance. And the reason why I want to do this is simple. When we'll be in production, we do not want a scenario where we have to use the mean and variance of the test, the full test set. So in this case, we have 80 by 8,000 by 21,000, and then we have 5,400 by 21,000. Now in the deployment scenario, would instead of having 5,455 by 21,368, what we would have is 1 by 21,368. And the way this scaling works is it makes use of each and every row to get a mean and a variance for each and every column. So for this column, for example, for this column, that's this first column, this first CPG site column, is going to make use of all this data to get the mean, which is then going to be used to scale this specific value. Now, in deployment, we do not have all this data available. We only have a single input or just a few inputs. And so what we want to do is get or be able to get a mean value, but this mean value is not supposed to come from the test data. It's supposed to come from the train data. And that's why we're making use of this train's mean value. The simple reason is that if you use the test data, or if you get the mean and variance from the test data, it's going to mean that we already have information from the test before even actually carrying out the test. So to avoid overfitting, we're going to make use of the mean and the variance from the train data, which is going to then be used when we are in the test scenario. And so that's why you see here we save this mean and variance data so that we could make use of that when we need that in deployment. So that's why this data is saved, and you could check that out. Once you've saved, you have this numpy files, and that's it. So we now have our train and train scaled and our train ages. That's it. And you could see that here. See now we have negative values, or we have in fact scale data actually. So we have our scale data, and then now we get into data splitting. So it's again simple. We have a random seed which we set the test set size, that's 10% of the full data. This is actually validation because we are not touching the test for now. So we have our x train x val, our y train y val, and then we pass in our train scaled, our train ages, and then this test set size with a random seed. Then we obtain our train and validation sets. So here we have our train 7,245, and then the test is 8,805, and then we have obviously the y train and then the y validation. So that's it for the section on data processing. We're now going to move on to modeling. In this section on modeling, you'll notice that we have two main models that we picked, XGB regressor and then the ridge model. Now, take note how we have those variations in the bits, the number of bits. So here we have XGB regressor with 6 bits, XGB regressor 8 bit, 10 bit, RGB, the ridge model 4 bits, 5 bits, 6 bits, 8 bits, and 10 bits. Now we used more, we tested more with the ridge because it's a smaller model and it trains faster and permitted us to actually try more of this. So getting into this XGB regressor, we are not going to take much time on this number of estimators, max depth, and number of jobs. The role or the aim of this part is to show you how varying the number of bits has to do with the model's performance. Now, the number of bits here is set to 6, and before we move on, you should understand that we have inputs in our case which are encrypted, and these are encrypted integers and not the usual float data that we are used to. And so because we're dealing with this encrypted data, we have quantized data. That's our inputs are then quantized such that they could be passed into our ConcreteML model. In this case, the XGB regressor. So you see here we have concrete XGB regressor instead of the usual scikit-learn XGB regressor. And we specify the number of bits, number of estimators, the max depth, and the number of jobs. So that's it. So once we define this model, we then go ahead and train. So we have our X train, we have our Y train, we have the validation, which we got already, and then the Y val. So let's run this and then see what we obtain. We get in this error. Let's get back again, and then we forgot to split the data. So that's it. And then we run this and see what we get. Training now complete. You see how those root mean square error drops as we go through our different epochs, and then you is actually going to be the same or similar with the 8 bits and the 10 bits and so on and so forth. So that's it. And then with a rich model, let's pick out, say, this 8-bit, this rich model 8 bits. Here we only have this number of bits to pass in, and then you just feed your model, and that's it. It takes just about 9 seconds, so you could try that out. So let's run this, and then there we go. So this is our concrete rich model. Takes about 9 seconds. With the concrete rich model picked as the final model, we'll then go ahead and specify our FHE directory. So here we have this weights folder, which for now is empty, and then we'll compile this our final model. The reason why we're compiling is because we want to have a model which can process encrypted data. So we'll run this compilation, and from there or from then we'll be able to pass in encrypted data into this final model or into our model, and then obtain results. So let's run this. We have final model, and then we carry out the compilation. Once the compilation is done, the next step will be to set up our development environment. So this is at the level of the client. Now we have always specified this FHE directory. That's this directory. Then we have our model, which has already been compiled, and then we save this. So let's run this. We're getting an error. It's not empty. Please delete it before saving a new model. So we'll go ahead and delete this and rerun this again. Now what we get is this client.zip and server.zip files. If you check out in the documentation, let's get to the documentation, you'd find that they explain clearly what this contains. So this client.zip contains the following files: a client.specs.json lists, or this JSON file which lists the secure cryptographic parameters needed for the client to generate private and evaluation keys. Then the serialized processing.json file, which describes the pre-processing and post-processing required by the machine learning model, such as quantization parameters to quantize the input and dequantize the output. Then the server.zip file contains the compiled model. So when we compile the model and we generate this server.zip file, it actually is now containing that compiled model. Now this file alone is sufficient to run the model on a server. After setting up the development environment with the FHE model dev class, we now go ahead to set up the client. Now with the client, we make use of this FHE model client class. We specify the path, that's the FHE directory path, which was specified previously. And then we have this key directory path. So you find that we have this keys client, which is going to be in this weights folder. Then we have the serialized evaluation keys, which we are going to use subsequently during the evaluation. Let's run this, and there we go. The next thing we want to do is check this out. So we check out this keys clients folder, and we find that here we're going to have our secret key. Let's open that. There we go. We have this. So here we have our secret key, which is going to be used to encrypt our input data and then to decrypt the result from the server. Now we're going to pre-process this new data. So if we have X validation, for example, here, we take this X val, we pass this into the quantize encrypt serialize method from the client, which we've set up already. Now this produces an encrypted information. So let's print out our encrypted data. Print that out. Let's keep this out for now, and then run this. So we encrypt the data, and then once the data has been encrypted, you see we have this encrypted data. So this is like let's print out our X file. Let's take this out from here. So take this, let's take that, and then let's just print it out this way. So we have this input data. See, this input data is converted to this encrypted data, and now this encrypted data is going to be run by our server. Now again, we set up the server. We specify just the FHE directory, which needs actually just this server.zip file. So this client zip and then the keys client, folder aren't necessary. All we need here is just a server.zip file, since as it contains our compiled model. So we load the server, and then we have this run method, which takes in our encrypted data and our serialized evaluation keys. So that's it. We now have the encrypted result. So let's print out encrypted result. And once we print out the encrypted result, we'll now go ahead and deserialize this encrypted result using the client. So let's run that and then see what we get. Print out the result, and there we go. So you see, again, we have encrypted result, print, and then we have the age which is predicted, and that's of 17. Now let's get the actual age. So let's get this actual age, take this off, or let's copy this, and then we'll paste it out here. We have Y instead of X. So let's get the real age and the actual age, or rather the input and the actual age. You see that it's actually 0. So we have actually 0, and then what we getting here is 17. So this model predicts the age of 17. Let's try it out. Another example. Let's say, for example, 2 to 3. There we go. We have this other input and output pair, 2, 3, and check that out. So let's print this out and see what we obtain. Now here we expect to get 42. So let's run this, and then you see we have actually 42.6. That's approximately 43. So the model does better with this other in this other validation sample. But what's important to note here is the fact that it doesn't need this input data to carry out the prediction or the inference. So all it needs is the encrypted data, and then once it gets the encrypted data, it's able to carry out the inference, and the client is able to decrypt this encrypted data to produce our output. We are now going to look at evaluation on the test data. So we have our test code and our test image, test ages data, which we've already created, and then now the number of samples is set to 100. We'll look at this, or we have this predict method, which is similar to what we would have with a classical scikit-learn model. And then we specify that FHE is set to execute. So here we have our FHE quantized model, which is going to work on or get our inputs and then generate this output. It takes a little while. For the reach model, the reach 5 bits, it took about 500 seconds. For the XGB, it takes more than an hour. So that's it. Then once we have this, we'll get into this calculate metrics method, which takes in the Y true and the Y pred. So what the model predicts and what is expected from it, or the actual ages. So here we produces the MSE, the mean square error, the mean average error, and the root mean square error. So once we get all this, we're going to print this out. Now, before printing out, we take note that each time we have a negative value, or each time the model predicts a negative value, we are going to set it to 0. So our outputs are clipped such that we do not have negative values. Then we'll now generate the, or we'll just have this visual here, which shows us the actual ages for all the different 100 ages, and then the corresponding predicted ages by the model. So let's run all this, and then we shall see what we get. Once we run this, we are now going to finally evaluate, that's get or calculate the metrics, making use of the model's predictions and the expected predictions. So that's it. So while we're waiting for that to run, we could check out this performance analysis, which I've done already on the different models and different bits. So the reach model, 4 bits, yes, predictions, and up to the XG boost model at 10 bits. Now this plot here shows us the different mean square error with respect to the bits. So for the reach, you see here for the reach, when you have at 5 bits, we have about 100 for mean square error, and then you see that from 6 bits upwards, there is no major difference or major drop in the mean square error. This is similar for the other metrics like the mean absolute error and the root mean square error, where after 6 bits, or as we increase the number of bits, we do not have a major drop in the performance. Although even as from 8, you see from 8 it's practically almost the same as that of 10 bits. So this shows us that as we reduce the number of bits, obviously the performance drops, because an increase in the mean square error simply means that our performance is dropping. But from a certain point, that's in our case about 6 bits, or would have even tried 7 bits. You could feel free to try out 7 bits. But in our case, from about 6 bits, we find that our model performs reasonably well. So we're done with calculating the metrics. You could find here the actual edges and their corresponding predicted edges. See that the model does quite well. We have mean square error of 21, mean average error of 2.5, and root mean square error of 4.6. We deployed this Hugging Face space, which could be used to test out our biological age prediction model. So first things first, we're gonna upload this CPG sites data first. So we just click on this. Let's get to downloads around the 18th. Okay, so we have age 40. So this is a person whose actual age is 40, extracted from the test data set. And then we have the better values in here. And the idea or the aim is to actually encrypt this data, pass this through a network, and then let a remote model predict the age. So the first thing, the next thing we're going to do is generate the private and evaluation keys. Please, okay, so we submit. So once you submit, you should get data submitted. Then now you generate the private and evaluation keys. So with this done now, with the keys generated, we'll now go ahead and encrypt the data. So also take note that this is similar to what we have seen already, or it's actually the same thing that's going on in the Hugging Face space. So we saw already that we could generate these keys, and then once the keys are being generated, the next thing we want to do is encrypt the data. So we have the better values which are going to be encrypted, and it's the same as what we had here already. So where we had this quantize, encrypt, serialize, it's the exact same thing that's going on here. So we have this encrypted vector right here. Then now we send this encrypted data to the server. So we have this client, and then we have the encrypted data, and then we send this to the server. Once this data is sent to the server, we have here data sent. We now run this or run the FHE evaluation. So we have our model. Remember, again here we have our server, and then we have server run. You see, we run this on encrypted data, and that's it here. So let's run this. This is going to take a while. Now note that we use the reach model here, and if you use the concrete XGB model, it's going to take more time, as it's a bigger or larger model. It's more performant, and it also takes more time. We use the reach model since it just takes 5 seconds and permits us to test out our model quickly. So feel free to modify this. You could get to the code here. Could get to the code. Let's take this here. Let me reduce this. Okay, so you could get to the code here on the files and then check that out. So you could check out the code, modify it, and then use a different model. So feel free to check that out. Now, once you have this generated, the output, or once you have the evaluation, you now get the data on the client side. So the model has evaluated, and then generated some output, which is obviously encrypted. We now need to get the data, and then we need to decrypt the data. So let's decrypt the data, which has been encrypted. Let's get back. Okay, so now after getting this data, which has been encrypted, we decrypt the data. And there we go. You see, it estimates age 33 for that specific person. So that's it. We now have our biological age prediction model from our data, and which or we have this model which predicts this output based on the encrypted version of our data, which is passed onto the server. So in conclusion, we have seen how we could use machine learning to predict biological age, based on CPG side data, and we have more specifically made use of Zama AI's ConcreteML to carry out these predictions on the encrypted version of our data. So with this, thank you for getting right up to this point in the course, and see you next time.